Hello everyone. In this video, I will go through the solution of assignment number 5 for module 5. As the first question, it assumes that we have a flip-flop named Pn. Pn flip-flop has 4 operations: clear to 0, no change, complement, and set to 1, when the values of the inputs P and N are 0, 0, 0, 1, 1, 0, and finally 1, 1. So when the inputs are 0, 0, I expect that the output will be clear. If it is 0, 1, I expect that there is no change. So the previous Q will remain the same. Complement, I will complement the Q. If it is 0, it will be 1. If it is 1, it will be 0. And finally, if I have both ones, it means that I want to set the output to 1. The question is asking about three different questions. The first one is to tabulate the characteristic table. The characteristic table contains or consists of the inputs that we have, which are B and N, and the output Q. I don't expect to see QT or QT minus 1. I expect to see the inputs and QT plus 1 in terms of QT. So I expect to have a table that will looks like this. We have two inputs, P and N. QT is the output, and it will appear here as a term of QT, which is the previous or the stored value of Q. Since I have two inputs, I have 4 rows, and I will populate them with all the possible inputs, which are 0, 0, 0, 1, 1, 0, and finally 1, 1. Depending on the description in the question statement, I figure out that when the input is 0, 0, I expect that I need to clear the output, which means I want the output to be 0. So I expect the output here will be 0. If the input is 0, 1, when the input 0, 1, then there is no change. No change means that the current, the next Q will equal the current Q. So Qt plus 1 equal Qt. When the inputs are 1, 0, 1, 0 means complement. So I expect the output will be the complement of Qt. This is why Qt plus 1 equal Qt dash. And finally, when the inputs are 1, 1, this means I want to set the output to 1. So the output here will be 1 regardless the current value of Q. This is what we call the characteristic table. This is what we call the characteristic table. So the characteristic table, I expect to see the inputs and the output in terms of the current output. The next output in terms of the current output. The second question asking about driving the characteristic equation. I will not be able to drive the characteristic equation without drawing the whole table or without the Karnoff map. To build the Karnoff map, I need all the inputs. The inputs right now are not just P and N, but P and N and the current state. So this table will be enlarged and will be something like this. Instead of have 4 rows, I will start to have 8 rows. Why? Because I want to see all the possible combination of the inputs, which are P and N and the current Qt. But it will be very easy to populate this table and calculate the output or get the output from this table. When P equals 0 and N equals 0, both equal zeros, the value will be 0, regardless the value of the current state. This is why I expected to see at the first row 0 and the second row 0. It will not get affected by the current value of the output, which is Qt. When the input P and N are 0, 1, 0, 1, it means the next output will follow the current output. So what is the current output? If it is 0, the output will be 0. If it is 1, the output will be 1. If the inputs P and N are 1, 0, I expect that the output should be the complement of the current Q. What is the complement of the current Q? If the current Q is 0, I expect to get 1. If it is 1, I expect it to get 0. And finally, when P and N are equal ones, both ones, it means the output should be 1 regardless the value of the QT, regardless the current output. So if it is 0, I will get 1. If it is 1, I will get 1. Now, after I built everything and I have the table, I can now build the Karnoff map. I will build the Karnoff map in terms of these 3 inputs. I have 3 inputs, so I expect that I will have these 8 cells. I will through the ones and zeros based on this, so you can figure out that at 0, I will have 0, 0, 0, 1, 2, 3, 4, 5, 6, 7. This is a mean term. 0, 0, 0, 1, 0, 0, 0, 1. Then I have 1, 0, 1, 1, 1, 0, 1, 1. So this is a Karnoff map that I have. I need to cover all these ones. How I will cover all these ones? I wanted to cover them in a group of 8, but I don't have a group of 8. I want to cover them in a group of 4. I don't have a group of 4. So I will cover them in a group of 2. Do we have a group of 2? Yes. We can cover these 2 ones together, and I will have this mean term. This mean term will not contain P, but it will contain both Q and N. So this mean term is NQ. So I need to cover these 2 ones. I can cover these 2 ones together. Don't forget that this column and this column are adjacent from the other side. So I can cover these 2 ones together like this, and I will have this mean term, which is P Q dash. So now I can say that since I covered all the ones, the characteristic equation will be Q of T plus 1 equal BQ dash plus NQ. Here Q is QT, which is the current output. So now we drive the characteristic equation correctly. The third question and the last one, show how the PN flip-flop can be converted to a D flip-flop. Easily we can get that from this characteristic table, but we need to understand how D flip-flop works. The characteristic table of the D flip-flop, I have one input, which is D, and one output that follows this D exactly. If it is 0, I will get 0. If it is 1, I will get 1. And we can easily understand that we get this 0 when I have both P and N are zeros. And I will get this 1 when both P and N are 1. So easily all what you need to do is to connect P and N together to the same input, which will be the D input. And this way I cover the whole question in question number 1, or the whole section in question number 1. I hope it is clear. If you have any question, let me know. I will go right now to the next question, which is the timing diagram. It assumes that you have an SR latch with enable control and clocked SR flip-flop. So I have 2 gates, SR latch and SR flip-flop, that is activated on the positive edge of the clock. The question asking about the output Q. Draw the Q for both of them given the following clock and the following values of S and R. And it asks you to assume that you start with input Q equal zeros. This is why I start with these 2 zeros. This is the output for the latch. This is the output for the flip-flop. I will go through the latch first, then I will go through the flip-flop. For the latch, we understand that the latch activated when I have a positive signal or I have negative signal, depending on whether it is activated on positive or negative. This question say it is activated in the positive. So I will act like this SR latch will work as far as the value of this clock is 1. So as far as I have 1, it is working. As far as I have 0, it is not. So at the current time we are here, I figure out that the clock is 0, which means it is not enabled. So I will keep the previous Q. Since it is 0, it will remain 0. At this time, we figure out that the clock starts to get activated Once the clock activated, it means the input for this latch will control the output. Since I have 0 and 0 in this SR latch, don't forget when we have S equals 0, R equals 0, it means I will keep the previous Q. So I don't expect any change to happen. That's why I still have these zeros. Now, the S is asserted to 1 while R still remaining 0, which means I have 1, 0. I need to do setting. Since the clock is active, I'm still reflecting the output for the corresponding input. So I have 1, 0. I expect that I will do setting for this output. So I have 1. At this stage, I still have 1 for S and 0 for R, so I'm still doing setting. At this time, the clock will start to go down, which means start to be inactive. Once the clock starts to be inactive, it means the SR latch will not work, will not respond to the changes that may happen to the input. So I will keep this 1 until I have another raised clock. So I will not make any change. I will not even look at the S and R. I will keep it 1, I will keep it 1, I will keep it 1, I will keep it as it is till I figure out I have a positive or high signal for the clock. This high signal means that the output right now will start to be the corresponding output for these inputs. What is the inputs right now at this time? The input for S is 0, the input for R is 1, which means I'm doing a reset, and I expect the output for Q to be 0. So currently, I expect that this signal needs to go down, and I will have 0, which is corresponding to the reset operation. After doing this reset, the clocks go down again. So which means this latch is not working. So I will keep the previous Q, which is low, and I will keep it until I have a rising edge for the clock. After having this high, during these high values of the clock, I will reflect the corresponding output for this current input. We have S equals 0, R equals 0, which means remain as it is, 0, 0. Then I have setting. I do set equal 1, reset equal 0, so I need to raise, and I will have output, which is 1. Then I have set equal 0, reset equal 0, which means keep the current Q. The current Q is 1, so I will keep it 1. Then the reset start to be asserted to 1, while set keep 0, which means I'm doing reset. Since I'm doing reset, this Q should be 0, so I will go down, and I will have 0 right now. Then I have 0 for S, 0 for R, which means keep the previous Q. The previous Q was low, so I will keep it low. Then I have a set equal 1, reset equal 0, which means I'm setting the signal. So it will raise, and I will have signal 1. At this point, I will figure out that the clock will go down, which means now this latch will not be active, which means I will keep the previous signal forever until I have another high pulse or high value for the clock. Since in this timing diagram I don't have any positive again, I expect that this one will remain till the end of the signal. So I will keep this one, keep this one, keep this one, we'll keep it until the end. Again, it's very easy. Since this SR latch, which means it will reflect the corresponding out, or it will work, or it will be enabled when I have high signal. This is why it will work at this time, at this time, at this time. Other than that, I will keep the previous Q. I don't expect any change to happen during this time, no change. 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 Let's go right now to the flip-flop. The flip-flop will be much easier because I only reflect the corresponding output for this input at either the rising edge or the falling edge. Here, clearly, I said that it works on the positive edge. So whenever I have a positive edge, I will reflect the output for this current input, and that's it. Any other change will not do anything. So this is the first rising edge. So I will keep the output the same till this rising edge. So it will be the same. And now let's think. If the current S is 0 and the current R is 0, and I will have a positive edge, which means I want to reflect the output. What would be the output? If S equals 0, R equals 0 means keep the same Q, keep the current Q. It was 0, so I will keep it 0. At this time, I will not reflect anything. Why? Because the flip-flop activated at the edge, not at the high pulse. So I mean activated at this time, but I don't care about any changes that will happen to S or to R as far as the clock does not have this rising edge. Where is the following rising edge? The following rising edge is this one. So I will keep Q as it is until I reach this rising edge. At this rising edge, I will go and look at the value of S and the value of R. I figure out that the value of S is 0, the value of R is 1, which means I'm doing a reset. So I need to make the current output equal 0. So I will make it 0. Since it's 0, it will remain the same. Again, no change will happen again until I have this following rising edge. So it will be the same till this point. I have a rising edge. This rising edge, say now you have to reflect the corresponding output for these inputs. What is the current inputs? S equals 0, R equals 0, which means keep the same. So I will keep Q the same, which is 0. And they'll figure out I don't have any other rising edge till the end of this timing diagram, which means the output will remain the same till the end of this timing diagram. Again, when we have a SR latch or SR flip-flop, they are working at certain time. The SR latch work, when I say work, I mean work properly, work as intended to happen. I mean enabled. So if I have SR latch, whenever I have a high signal at the clock, it reflects the output, follow the input. But if we are talking about flip-flop, that this happen at certain time. What is this certain time? When we have this falling edge or rising edge, depending on the type of this flip-flop. In this example, we have SR latch that enabled when the value of clock is high, and SR flip-flop that enabled when we have the positive edge. For the latch, for the SR latch, the output will follow the inputs as far as I have this high signal, at this high signal, at this high signal. For the flip-flop, the output follows the inputs whenever I have this rising edge. So at this point, and at this point, and at this point. I hope this video make the solution for this assignment clear. If you have any question or any thing you wanted to clarify, please let me know. See you.